So, today we will just see the few equations to calculate the elastic settlement of shallow footings or spread foundations, followed by pile foundations. We will start up the actual course. We have seen a few equations earlier on in the last class regarding empirical formula for interrelating the bearing capacity and settlement, which is basically an empirical relationship you have to use carefully. But this one, just now what we are going to see is the reason why we need to know the settlement, as I mentioned in the first few classes. Basically, the reason for foundation is well known, the load transfer to the substratum without affecting the superstructure behavior and the acceptability criteria. That means the response of the structure needs to be within the limits. One of the response for most of the structures is the vertical displacement, which is substantially important because it will hinder the operational requirements of the, whether it is a building, bridge or offshore platform. So, basically that is the idea. So, the bearing capacity equation as derived by Terazaghi as well as modified by others does not really have any relationship with respect to the settlement criteria or the relationship between the capacity and displacement. Now, we could possibly relate by doing some relationship with respect to the displacement and the capacity by doing a load test. For example, when you actually want to establish that such relationship, you can go to the field, you carry out load test by means of applying external load and then record the displacements and then derive at relationship. It could be linear, it could be non-linear depending on the type of material. For example, steel, when you do such thing in a tensile test, you actually get a stress versus strain, load versus displacement. So, in the steel material, for substantial portion of the strength, you have a relationship which is very straightforward, linear. Then after that it becomes elastoplastic, whereas for soil, you could see from this picture just now, we have two different class of materials, coarse grind versus fine grind. Coarse grind, you have cohesionless soil, basically a grind size material like sand, or clay, which is fine powder plus mixtures. So, you could see distinctively a behavior difference between sand and clay. Sand behaves almost like similar to perfect elastoplastic. You can see just straight line and then just straight away going to 100% plastic. That means, as long as the particle gets displaced or dislocated due to loading, they simply fail and you can't repair them, it will not be able to come back. So, a permanent deformation. Similarly, clay, instead of going linear relationship, because of the type of behavior, you have compressibility and you see almost non-linear. So, this is the thing that we want to relate and find out how do they behave in case of a multi-layered soil. You are not going to have complete sand or complete clay for throughout the depth of the bearing stratum. So, you may have various layers of different materials, or even within one layer you may have a mixture of materials like sand and clay. So, we need to just assess. So, what we really need is one important property which I have given you a big table few classes back, relationship between SPT value and modulus of elasticity, which is very very important, because that is what is required to establish the stress strain characteristics or load displacement characteristics. The immediate concern for us is basically the immediate settlement for any type of foundation as soon as you complete the construction, due to its own self weight or the loading just occupied by the structures in immediately after the construction completion, or the consolidation settlement basically after a longer period of time due to consolidation of clay type of material, where you will see that substantial portion of the settlement is taking place. So, we need to just see which one is going to affect it. For offshore structures, we are not really too much worried about the consolidation settlement because we have a different type of foundation, which is very much essential for onshore type of structures where you have shallow footings or small different foundations. But the immediate settlement is very much important for us as we place the jacket on top of the seabed with no pile foundation, because we have just a spread footing or a mat foundation, I would say. When you place the jacket on seabed, the immediate settlement immediately after the placement is very much important, because after few hours we are going to do piling. Once the piling is done, the jacket is secured well with not much going to happen afterwards, because the pile is very deep foundation taken to bearing stratum. So, the temporary stage where the jacket is placed on seabed, and basically we do not want the jacket to settle too much, so that your water level relationship with the jacket top is not changed. Okay, few hundred millimeters is acceptable, but few meters is not definitely going to be a acceptable criteria. So, how much is acceptable is supposed to be decided by the engineer, because you can always adjust. If you know pre-hand that you have calculated deflection is 500 mm, you can actually design the jacket 500 mm higher. So, you know very well that at this particular site the jacket is going to settle by 500. So, you elevate your superstructure interface by that much. So, that is the idea of this, why we need to know the settlement for us, especially for offshore structures, is to establish the benchmark levels for the interface between jacket and the substructure. So, we will only look at quickly how do we estimate the immediate settlement on two classes of soils. The first one is the the general elastic formula. You could easily see this is very similar to derivable from basics of stress strain criteria. So, this Q naught is nothing but the applied pressure due to the structure placed on top of the soil, and mu and Es is the elastic properties, Poisson's ratio and your elastic modulus. The whole thing depends on this particular value. The larger it, the smaller the displacement. So, basically that is where the whole matter relies on. So, when you are doing a soil test in the field, you get the SPT value relate to Es, or if you take a soil sample to the laboratory, you do a triaxial test, you could possibly get the Es values from there. So, basic idea is deriving these two properties is very important, remaining is only based on geometry and the type of loading, and the influence coefficient just as a matter of location and basically the shape of the foundation. So, these two coefficients can be either calculated by equations given here, little bit complex, is actually derived from Boussinesq's equation for stress below the load applied on foundation. It is a simplified form. In fact, if you look at Boussinesq equations, you will have several cases, whereas I have only taken a case for displacement at the corner of the foundation or displacement at the center of the foundation. So, basically 2 points, and this particular equation is just basically derived for flexible type of foundation, means it will have elastic deformation, or you can also find out just taking a slightly reduced by rigid foundation. So, you could do that, but ultimately what we will require is the applied pressure 1 minus mu square divided by Es, which is very similar to the stress strain equation for steel, except that you are going to multiply by the influence coefficients and the shape factor. The shape factor can be calculated as proposed as by Stenberg, Brunner, using these equation F1 and F2 can be found from these two equations for different locations. This is what was proposed. Basically, alpha is 4, m dash and n dash is the normalized length and width, and for calculation of settlement at the corner of the foundation, which is at 4 corners, any one of them, if it is a rectangular, alpha is 1 and m and n is. So, you have to substitute these values of m and n to calculate the F1 and F2, and F1 once you calculate, you can calculate the shape factor. So, basically that is the idea, very similar to we were having shape factor for bearing capacity for circular, rectangular and square shape, and then we need to have a calculation for the influence factor. This is basically the as you go down along the depth from the base of the foundation, you can see that the influence of the soil pressure is reducing. I think we have seen this one the first few classes. You can see that as you keep going down, the soil pressure get dissipated, means the spreading is more, the average pressure will be less. So, then you will have a effect on settlement will be also reduced. So, this charts I have just taken from the original paper from Stenberg and basically plotted with respect to h is the depth, L and B is the length and width of the foundation. For different values of L by B, I think there are 4 charts. Basically, you can read basically here L by B is 5. So, you can read that chart and get the IF coefficients, and the basic idea is the calculation of settlement can be easily found. So, main matter is the elastic modulus. Now, if you have a realistic soil, normally you do not have a single layered soil in any type of bearing stratum, you will have multi layered soil. So, what we normally needs to do is try and find out an average, like what was proposed by Bowles as early as 1980s, where you can find out a weighted average with the layer thicknesses available H1, H2, H3, and then you do the each layer modulus of elasticity and then find out the weighted average. By doing this, you are taking the influence of these lower layers in the settlement of the foundation at the top layer. So, basically as the pressure goes down, you can see that the effect of that will be taken into account by taking the average modulus. There are several techniques available. One of this is the approximate method, where you can do this, or you can actually calculate by FE analysis by modeling the whole soil stratum, which will be time consuming. Instead, the influence can be taken care by averaging the modulus of elasticity, and go back to use the same equation. What you see here, instead of ES, you will be using the, it is very similar to arranging the springs in series. You know, you have a soft spring, slightly better spring, and so the net effect of all the springs together is basically taken into account in the settlement of. The last one is very important, because most of the times in mud mat type of foundation, first 2-3 meters will be soft clay. After that, many occasions you will see a sand, and then you will have strong layers. So, if you only take the soft clay, you will see that the foundation is going to settle by substantial amount, but of course, that pressure, if it is soft, what happens is the soft material transmits the pressure to the next layer starts going down. So, that is basic idea is how much is that, is it same as the soft layer or slightly better off than the soft layer. So, that is why we need to take this into account. So, I think with that we will limit, we will not go into consolidation settlement, we may not require for our offshore foundations, and I will quickly jump on to the pile foundations, which is the primary part of our course. So, basically we will be looking at substantial period of time in number of classes for understanding the pile behavior. We will apply what we have learned for the last few classes on bearing capacity of shallow or spread foundations and settlement, and apply that principle to deeper foundation, which is basically the pile foundation, and we will focus purely on driven steel pipe piles, not the concrete piles. I think we have just got introduction of concrete pile last time, but we will not focus so much as it may not be applicable to offshore structures. So, we will quickly look at axial capacity first for the first few classes before we go on to lateral capacity. The axial capacity consists of several things, we will see one by one, as starts from pile group arrangement, and then the load transfer, how it happens, I think we have seen that, and then the axial load transfer capacity by means of assessing the soil characteristics in a layered soil, and then estimation of skin friction, estimation of end bearing, which is very similar to what we have done just now for a shallow footing. Shallow footing, what we have is only end bearing, means is a contact pressure between the soil and the foundation. So, here in pile foundation also you will have that. In addition, because the arrangement of the foundation is such that you may get a frictional resistance between the pile and the soil. So, you got two components to estimate, and then we look at the factor of safeties as per the codes, and then there are corrections and then various other methods. Finally, we will come down to the load displacement relationship, which is very important. Just now we have got bearing capacity for shallow foundation, we have estimated as vertical displacement by means of a simple elastic theory using modulus, but we have never related them, and most of the cases it is not related. When you are designing a building, we do not relate them so much, because we calculate the capacity, we come back and establish the settlement. If the settlement is higher, we have two things to do, either reduce the load or increase the foundation area. That is what we iteratively do in your design of onshore structures, whereas in offshore structures such iteration is simplified by making a relationship between the capacity and the displacement, so that you can use in the starting time itself what is the required capacity for a given settlement. So, just take the graph, even if it is nonlinear, you can program it, and that is the idea behind establishing such relationship, basically called T jet is the vertical capacity in skin friction and displacement. Similarly, Q jet is the end bearing capacity and the corresponding settlement. So, that is the idea behind. Lateral capacity also as important as axial capacity, as we discussed earlier. The offshore structures are subjected to considerable lateral loads. So, what we need is to make sure that the soil capacity is taken into account appropriately to resist the horizontal forces, to make sure that the response is calculated. So, here we have several ideas, in fact a lot of ideas I would say. I have just collected reasonable information which are relevant to offshore structures, and then try to go from there. In here we also establish the relationship between the lateral load and the lateral displacement of the soil material in various types of soft clay, stiff clay, sand, and then due to cyclic load, as you know, the wave load is going to be cyclic, unlike gravity loads is static. So, what happens to the soil when you are actually keep on moving back and forth? The soil gets remolded, soil gets loosened, or may actually lose the strength completely, and as it goes progressively, the top soil near the seabed may actually get looser very fast compared to the soil below. So, as it goes progressively, when the soil is top layer is getting reduction in the strength, what happens to the next layer and next layer, and so. So, how long it will take, because the structure is going to be there for several years, and you can see progressively degradation will happen. We call it the soil degradation due to cyclic loading. So, all those things we need to learn. These are all something special for offshore structures, which we normally do not look at it in onshore structures. So, we will just quickly go through the vertical foundation. I think by this time you are familiar with the foundation types for offshore structures. For sure you will not have concrete piles, you will have steel piles, and that too open ended sections. That means, take a hollow circular section, both ends are open and start driving down into the ground. So, you can see this is not a displacement pile, but partly displacement pile. As you are driving, the portion of the material or the wall thickness has to be displaced, but not similar to a concrete pile, where if you have a full concrete pile driving into the ground, the whole soil forming the cross section of the pile has to be displaced. So, you will not see too much of soil displacement in this case, but of course reasonable amount of compaction will happen inside the pile, because the soil is getting squeezed in between. So, open ended steel tubular pile driven into the ground, that is first case. The second case, open ended steel tubular pile, but not driven into the ground, but bored and placed into the ground and then grouted. I think we discussed about these two cases. Wherever you have encounter of very hard soil unable to drive, for example, what you can do? You can still do this by making a drilling, place the pile and do the grouting. So, the soil to grout interface, grout to pile interface, whereas the actual driven pile you have a soil to pile interface only. So, basically 99% of the time we have driven pipe pile directly into the ground. The drilled and grouted piles very rare, because it is very expensive, number one, and not preferred by anybody, including the owners, because it is quite time consuming. To drill 100 meters of depth, you can imagine it takes a considerable amount of time and effort. So, you see these pictures here, I have just given you the plan view of the jacket, hope you can understand. Normally you will have 4 corner piles in each jacket. In this particular case, because of loading is substantially higher, you have several choices. For example, you can have, instead of one pile of 1 x diameter, you can make the one pile double x diameter, isn't it. So, basically you can do that, means diameter can change, but how much diameter is an acceptable criteria to practical installations, which is something is very easy to find. The equipment availability, is the most important criteria. So, normally the pile diameter does not go beyond 96 inches, at least in this region we have not seen any piles having diameter more than 2.5 meter. So, you can imagine, you do not think about driving a pile of 5 meter diameter, 10 meter diameter. So, forget about such type of ideas. Normally about 2 to 3 meter is the type of diameters, 1.5 to 2 meters, 2 meters to 2.5, that is the kind of range. So, when you are designing a pile foundation, average diameter or the maximum diameter, you should remember 2.5 meter max. So, when you exceed such a criteria of 2.5 meter, you have only one choice. You can increase the diameter, the length of the pile, which is again going to be a problem, because going too deeper also is going to be installation related issues. So, that is the time you go for the third choice of increasing the number of piles around the load transfer corner. So, you take this corner, for example, you go to this picture, the loads were substantially larger in that bigger platform, you put several numbers of small diameter and a limited depth foundation, which does exactly the same purpose. Individual one has got some capacity, cumulative addition of all of them. We will see later whether that cumulative effect is same as the group effect, which we call it group efficiency, which we can discuss later on. But the idea is splitting the loads into several subgroups like 1, 2, 3, 4, and then each group has got individual piles forming total capacity. So, that is the idea you need to keep. To do that, you need to know what is the practical range of values, diameter range 1 meter to 3 meter, depth range say from 50 to 100 meters. Do not design a foundation with 500 meter penetration, then it will be impossible to install. So, you need to always think about how it can be done, whether it can be installed or not installed, that is the idea that you need to keep thinking. So, that is the reason why you can see that different configuration, there is no fixed configuration to any type of jacket, because the loads and the type of soil in individual location is different. So, that is why you see here in this particular, the jacket size seems to be similar, not very big different in fact, but you can see here number of piles are more, number of piles are less in each corner. Distribution of the piles to the middle also has been done. So, there is no fixed rule that if it is a 8 leg jacket only 2 piles per corner or 4 piles per corner, all depends on the configuration of the superstructure. So, the pile group arrangement is actually something that will be arrived by the engineer or designer depending on the situation, depending on the ground conditions, predominantly affected by the ground conditions. How the load transfer is predominantly happening for a offshore type of foundation. I have just drawn the part of the jacket and part of your skirt pile. So, this is basically the jacket leg and this is a skirt pile. I think most of you will remember, I have shown you some pictures that the load from jacket has to transfer through the plated connection to the outer shell and then to the pile, and predominantly goes through friction. Why did we choose to go for pile foundation? Is to transmit the loads to a bearing stratum, which may be far away from the seabed. That is one of the reason. Second, you could see that when you are doing this, you also get a substantial frictional resistance from the pile surface, both inside as well as outside. So, as you are trying to go and try to search of bearing stratum, if you never find, what will happen? For example, I want to look for the layer where the soil is very good. When I try to penetrate the pile down there and want to get a maximum bearing from the soil itself, but if that such layer is very far, 500 meters away, are we going to search in and go down to 500 meters? Not really. So, what we will do is, we will terminate the pile wherever and take into account the frictional resistance of the pile surface, and the cumulative effect, if it is sufficient enough to take the loads, will stop the pile. So, there are two types of pile foundations. One is the end bearing piles or the frictional pile. You could go either way, or you can have a combination of frictional pile plus the end bearing, depending on where you terminate the pile itself. So, it does not mean that we will always keep in search of the layer that takes the full load, very similar to the shallow foundation. Remember, when we were looking at the shallow foundation, we highly rely on, or in fact 100% capacity is coming from the contact pressure between the foundation and the soil. Now, if you do not have enough capacity, you do increase of soil foundation interface, that means make the bearing area larger, or you actually dig the ground, go deeper and make the foundation there. That is what normally is being done. But in such cases, if the bearing layer is very far, that foundation will not be suitable, because you can't excavate 100 meters of depth and go and start making your foundation there. So, that is the time you change your idea to, instead of a spread footing, make a smaller foundation size and go down and try to. So, the pile foundation concept is very clear. We are looking for a solution where the load can be distributed to various layers as well as to a bearing layer, even if it is at a slightly longer distance from the seabed. So, you can see here the arrows indicate is the friction between the material, which is a steel material, to the soil. Similarly, on the inclined pile, you can see here on the batter pile, main pile, it is exactly same, only that the pile is not vertical, you can see here slightly inclined. But what we are looking at is the frictional resistance between the pile and the soil. As early as Terasaki time to the recent times, different ideas, different conceptualization, how the load transfer can happen. You can see the first one is very similar to shallow footing. He has come up with an idea exactly same, the distribution of stresses beneath the pile foundation, except that the load is carried by the stem and goes down to a terminating layer, and you just draw your pressure diagram and try calculating your capacity in a similar way what we have derived few classes back, exactly the same idea. And you could see here on the right hand side, the overburden pressure on the sides of the pile is the very important criteria that he has considered. So, the more the overburden pressure, the less the chance of pile displacing the soil around and fail. So, that means the deeper that we go, you get a very good capacity at the end. So, that is basically the end bearing. In addition, you may also have the pile trying to receive resistance from the side of the soil, which depends on the relationship between this soil and this soil. Imagine I have a soft clay and then very good rock at 15 meter below. I take the pile foundation and install. When the pile reaches the 15 meter rock foundation, the total load transferred to the pile will straight away go on resisted by the rock, because the rock is high stiff compared to the soft clay, compared to the material or the foundation material is steel. So, if you look at the relative stiffnesses of steel, clay and rock, what will happen? Full bearing will be taken by the rock itself, not by clay. So, in such instances, skin friction shall be ignored, because it is not able to, the soil is unable to take it, because the full bearing is coming from, because the rock is very strong. So, that is why the relationship between amount of skin friction and amount of end bearing is going to be a topic where you will not find a solution. In fact, it is a iterative technique. How much load is transferred or shared by the skin friction, how much load is shared by the bearing is depending on the type of soil, especially if you have the difference is very large. The material, end bearing material to skin friction material, if the stiffness is too large, is going to be very big issue of finding the sharing. But most of the offshore foundations, we have the soil, we will not go for pile foundation if you find a rock very early, we will go for different type of foundation. So, that is why you do not find such problem. So, if you go to Meyerhoff, from the concept of this, he has tried to distribute more friction come bearing to a slightly higher part of the soil, followed by other researches. You could see different ideas and different configurations. Of course, we still go back to Terasaki, slightly modified, because all other proposals were not so good. So, the first proposed by Terasaki is still used by many codes, only with some modifications. So, how do we estimate the capacity of the pile in this case capacity of pile does not mean that the capacity of steel material. In this case, when we talk about axial capacity of driven steel pile means is the soil capacity, not the pile capacity. You understand very carefully, pile capacity is different. Pile capacity is the structural capacity of the section, which we have learned in the structural mechanics or design course. In here what we are talking about, this axial capacity means the capacity of the soil surrounded in the vicinity of the pile to take the load with whatever displacement relationship we are going to calculate. So, in this process what we are looking at is the skin friction between the pile surface, which is a steel surface, plain, there is no roughness on the surface except the actual surface structure of steel. We do not go and do any roughening exercise as we think about making the friction higher means, if you have a roughened surface, what will happen? You have a better friction, but we do not do it because it is also expensive. So, the friction resistance between steel pipe, plain pipe as made from the mill to the soil, it can be sand or clay, it can be any combination. Estimation of bearing resistance at the bottom, which is basically up here at the tip, how much it can rest, how much it can give you the vertical capacity in terms of end bearing, very similar to shallow footing, how much is the capacity at the bottom. So, which is basically we call it bearing resistance or sometimes we call it end bearing, either way both denote the same. And then determination of plugging or non plugging, this is basically what is really going to happen. We need to just, we will talk about this today, that what really happens when you take a open ended pipe and just drive into the ground. When you drive into the ground, you have a resistance from the external surface of the pile as well the interface between the internal surface and the soil, because the soil is inside. As you drive, soil also goes inside of the circular section. Now, when you keep driving, you stop and then just pull the soil, what will happen? Pull the pile will try to come out, and you can try at easily any place, even you can take a small pipe. Once you drive, you take the pipe out, if the soil falls down, when you pull out the pipe, what will happen? The soil also tries to fall down. Why? If the friction between the inner surface and the soil is very high, if the soil friction is very high compared to the weight of the soil itself, what will happen? The soil will not fall down, the soil will be there, because the frictional resistance compared to the weight of the soil is larger. Then we actually, when you pull out the pile, the soil will be still inside, which means that the frictional resistance is very large inside compared to the weight of the soil, which we call it plugged pile. The pile becomes, or the soil becomes part of the pile. So, though you are driving a open ended pipe, after reaching certain distance, what happens is the soil gets plugged inside, becomes part of the pile, then the behavior will be as much as driving a concrete pile with no opening, that means it is a solid section you drive. So, you can imagine when you try to drive a pile open ended section, after driving certain distance, what happens? The pile becomes difficult to drive, because the soil inside becomes part of the hollow section. So, we want to see whether we are getting into the situation. If you get into the situation, may be very difficult to drive. So, that is why we want to find out whether plugging or unplugged pile we want to determine. Why we need to do this? Because if you have a plugged pile, the end is closed, though you driven the pile without end close, but actually achieving slightly deeper, you have got a full end closed, because the soil becomes part of the pile. Now, when you apply the capacity, you will apply the capacity to the full area rather than the steel area. So, that is the idea behind it. So, we want to find out when it will happen. The easy idea is the frictional resistance inside is greater than the weight of the soil, then plugging. So, you can easily find out, what is the capacity, what is the weight of the soil. Weight of the soil is easy to establish, because you can find out height multiplied by the density. So, very easy, as long as, so So, height times submerged density because all our cases are submerged cases. So, basically the plugging or unplugging is nothing but soil becomes part of the pile after driving is supposed to be a criteria. Then estimation of axial capacity is easy because now you have external friction, internal friction and end bearing, or external friction and only the end bearing depending on whether the pile is plugged or unplugged. You can see from this picture, that is what the idea I was trying to explain before you see this picture. On the left side you have unplugged case, I think is easy to understand, no, because you got a friction outside, friction inside and bearing only through the annular area of the steel pipe wall, which you can calculate easily. If you know that outer diameter and wall thickness, you can find out what is the area times the bearing or the unit bearing, very similar to the bearing capacity you calculated for the footing size, except that it is going to be deeper. Whereas, when you come to the right hand side, where you can see here external friction and full end bearing, but the soil as part of the pile. So, even if you apply this pressure, what should not happen? The soil plug should not get moved away, it should have sufficient friction. You understand the idea, no? When you can, it is not only that the soil plug has got sufficient weight, but also should have sufficient friction. For example, if you want to take end bearing like this, you apply the end bearing, what will happen? If the internal friction is smaller, the whole soil plug will get moved away, which means that you have underestimated the or overestimated the bearing capacity. So, that is the plugged case is nothing but soil plug forms inside. Suppose you want to actually make it artificially, how can we do this? You want a very good bearing capacity at the end, so you could also do that. You just take out the soil from the pile inside by using several drilling techniques. After driving the pile, remove the soil and just put the concrete inside. In many cases we do this whenever you require additional capacity for a repair type of work where the capacity is not sufficient, you remove the soil and then pour concrete inside full. As soon as the concrete gets set together with the pile, then it becomes actually a solid pile where full capacity from end bearing can be achieved. Some cases, whenever we encounter such problem like capacity is not adequate, then we try to do this. So, formation of plug by nature is simply we can leave it, or formation of plug by artificial means to establish the higher end bearing capacity can also be achieved. So, pile plugging or unplugging is something that we need to understand, because this is where we are going to differentiate between the capacity, vertical capacity. That is what I have just explained so far, when and where it will form. As long as you know the internal friction, weight of the pile, weight of the soil, and compare it, and if the weight of the soil is higher, then the friction capacity it will become unplugged, or the other way around, friction capacity is higher and the soil weight is lower, then you will have a plugged capacity. So, you need to establish this first before we go into the. Now, there is just one difference, whether we go back to this picture very nicely drawn, that you can see the internal soil plug is coming to the level of the external surface of the seabed. Theoretically it should be like this, when you just take a thin cell, you drive into the ground or drive into a material, you are supposed to have levels internal, external same. As you drive this pile by vibration, there are several things to happen. For example, if you take a sandy material, granular material, you try to drive this pile into the ground, what happens is the soil inside is confined, cannot move anywhere, but the soil on the top always going to be loose. As you try to drive and vibrate the soil gets densified and may reduce in height, and this is what was observed by several field tests, especially when you are driving the pile in a granular material. They find that the pile plug is not coming all the way to the level of the external soil surface, and that we call it pile plug ratio. Basically the pile plug ratio equal to 1 means the pile length into the soil and pile plug length inside the pile is same. If the pile plug ratio is 90%, 80%, 40%, depends on how much pile plug. In that we can see here one more important thing is soil at the lower part of the pile gets densified, soil at the top part of the pile may not be that much denser than compared to the. So, you can see here there is a because of the disturbance that you are doing to the soil during driving. So, he has proposed a certain form of equation depending on the pressure or the vertical pressure at the soil locations. He derived a certain relationship which will give you the pile plug ratio. So, as soon as you drive the pile you measure the length of the pile soil plug inside and put it into this equation. So, you can derive whether you will achieve full end bearing capacity or there may be a reduction in the end bearing capacity, because when you apply a end bearing capacity of this much, if the plug is only 50%, you are not going to achieve it because the length of the plug is less, the end bearing capacity is going to be. Now, how do we calculate the end bearing capacity reverse? For example, the end bearing capacity can be calculated based on what is the type of soil below. If you have a rock, end bearing capacity is capacity of the rock itself, but also depends on the frictional resistance of the pile soil interface plus the weight of the soil. When you add them together, the end bearing capacity must be lower than that. If it is higher, the plug will move upwards. So, though we have a very good material here, very good bearing stratum, if the pile plug soil plug inside plus the frictional capacity is not sufficient, you cannot take that much bearing capacity at the bearing stratum, because the plug will start moving upwards. So, that means the end bearing capacity is limited by the soil plug weight and the frictional resistance of the soil itself. So, that is what he is trying to derive by the reason why he has given this exponential formation is the reduction in the frictional strength as we go down.